All right, cool. You all seeing my screen?
Yes.
All right. So I guess I can put this first poll into the Slack. How'd everyone do? How was lesson 2?
Pretty good.
Good? We may have a live debugging session here because I was never able to get to the accuracy levels that he was able to get in the videos for some reason. Let me change my camera too. All right. Did anyone run into that issue?
For the dog breeds?
For the dog breeds
Okay.
in particular, yeah. I
tried another one, a different set from Kaggle. The plant seedlings, yeah.
Okay.
Sam, I investigated a little bit about the resizing issue we talked last time. And so maybe I can tell something about that. Can you hear me?
I'm back.
I can hear you.
You can hear me now?
Yes, right. So, okay, Sam, I just said that I investigated a little bit this resizing topic we talked about last time.
Okay.
And so maybe I can show just a little bit, 2 minutes or something, how it works and why you can use different image sizes.
Okay. Yeah, let's start there. Do you want to share your screen?
No, you can just open the link I posted in the, that's enough.
Okay.
There's a picture. Okay. So that's a picture of basically how a convolutional layer works. So those blocks on top are the RGB representation of the picture. So each of these blocks is one number, red, green, or blue, of 1 pixel of the picture. And this is kind of a 3D matrix, or what's called a tensor. And those operations that swiping over the image is what's called filter or kernel or feature detector. There are different names for that. And it's really just basically doing a weighted sum of the numbers, adding a bias value, applying a nonlinear function. But there will be more on that on the next course, so I'll not go into detail on that. What you see on this picture is basically a convolutional layer with 2 filters. So it's done 2 times with a different set of weights. And those balls that are appearing on the bottom of this picture, that are really just the numbers that are generated by this filter operation. That's called a feature map. And in this case, you have 2 filters, so you have 2 feature maps. And yeah, after that, you would do something that's called max pooling, which is basically just downsampling those feature maps to get them smaller, to reduce the size. And so you do that multiple times on the filter maps. You do it again and again and again. So and in the end, you have a deep convolutional layer, which is pretty narrow. And that's basically how it works. But there will be more on that in the course. But what you, so when this somehow makes sense, you will see that the size does not matter for this operation, right? So when you give it a bigger picture, it's really just creating bigger feature maps and propagate that through the network. So it does not care how big the picture is. But in the end, of course, you want to have class probabilities. And what people used to do is really just collapsing these feature maps in the last layer and to a big vector. And then just append a dense neural network to classify the picture. And when you do that, of course, you constrain the size of the last layer and also all previous layers. And in more modern architectures, you do something what's called global average pooling, where you just apply a one-by-one convolution in the last layer to really just extract the numbers of the last feature maps. And then, so when you have 64 filters in the last layer, you get 64 2D feature maps out of this. And then you really just take the average of all of those feature maps. And no matter how big those feature maps are, it always results in one number. And in this way, you kind of, you can always attach the same dense neural network at the end, the same size for the neural network. And you basically kind of decouple this convolutional part of the network from the classifier in a way that size does not matter anymore. And that's what's done in modern architectures. And so I asked myself why they did in the ResNet paper, they did all the same size for the pictures. And also we in our notebook, we really had just one size for all the pictures. And that's because you do something what's called mini batches, where you show more than one picture at a time to the network in the learning process. And when you do that, you of course need to have the same size for the pictures. But you can always change the size when you do a new learning, for example. So you can use 224 for all pictures or 299 for all pictures. And that's why you scale and crop the picture, although the network could potentially handle it without sizing it. And I have a link to a blog post where this progressive resizing technique that Jerry mentions in the course is discussed. So if you're interested in that, you can read that. I will post the link. And yeah, so it is possible to use different sized pictures. Yeah, that's pretty interesting.
Okay,
yeah.
cool.
So different size pictures, there will be not with the Fast.ai library, right? You would need to use your own code, I guess, because Fast.ai converts everything to one size, right?
Yeah, no, you're just really just resizing all the pictures to one size because you show the pictures in batches. You don't show one picture to the network, but you show 64 or 128 pictures. And when you do that, all those pictures have to be the same size because the tensor has to be the same shape.
Right.
And that's why you do this resizing. But when you really just want to inference one picture, you can give the network a size as you want. So it does not care about the size in this case. That's
that.
Oh. That's loud.
Andrew, I think you're connected. Your audio is connected on 2 channels and it's causing some feedback.
Oh, okay. Sorry about that.
I muted you on both of them now.
Okay. So yeah, but technically it can handle any size of pictures, but when you do training, you do that in batches, and inside those batches, you have to have the same size for the pictures.
Got it. Thank you.
Yeah.
There was a question about from Kazakhs about learning rate. Lesson 1, initial graph was empty, so could not see the slope he showed when picking the number 0.02. Why was it empty? Could it be that the validation set was too small, only 8 images? Can PNG images be used? I remember reading something about the JPEG, or maybe we talked about this last week about JPEGs versus PNGs. I forget the result there. Has anyone used pings with with training with Fast.ai?
No, I didn't. No.
And I'm not sure why the I've not run into the learning rate graph being empty either.
I had such a situation. I was reading also some forum posts on that. Some people had the same. And I think I saw Jeremy replying that I think if you have like a small number of images, then I guess you would need to change the batch size to smaller number as well, because there's some interaction there. And by default, it's like too big number to give you the graph, I think. I'm not quite sure, but
it's 64 by default. I looked into the function.
So when you have like small number of images and there is some interaction there, and possibly you would need to change the batch size to smaller number to give you the graph of the learning rate finder. I think so.
Let's maybe do a sound off of which of these problems folks worked on and with lesson 2. I tried to do the dog and cats with mixed results. It worked, but I didn't get anywhere near the accuracy that he was showing in his videos. I was getting like 90% and he was getting like 99%. What other things did folks do? Did anyone do the satellite one? Lenny did satellite. How about Kai? Which one did you say you did?
I did plant seedlings. I think 12 or 8 or 12 different plant seedlings, like photographs from the top.
Okay.
And yeah, I think good at Kaggle was like 98%, and I got up to 95%.
Okay.
So top third maybe.
Matt did cat and dog as well, but had much lower imagery. Still training at the 256 image size.
So this plant seedling thing was 1.6 gigabytes. That was, so did not took too long for training. So that could iterate a little bit more.
Yeah, the training on, at least the way I was doing the dogs and cats, was relatively quick as well. I don't know what type of, but this was mostly with the pre-compute stuff. Actually, even with pre-compute off, it wasn't all that slow. Anyone do anything else besides from the satellites, the dog breeds, plant seedlings? Anyone try the Yelp competition? I wanted to try that, but didn't get to it.
I tried the MNIST data set, which is the handwritten digits. So for that, you need to convert the array of numbers into JPEGs, but you can also download them from some place on the internet. So that's what I did, and it worked quite well as well. Yeah.
Okay. Cool. There's also this on learn schedule plot that issues with the learning rate. Oh, this is in the Slack. Yeah, that's not going to work. A couple of different solutions. Oh, okay, the long way around to a link. So an article on learn schedule plot doesn't show anything. Yeah, so this was the dog breeds one. And I got as far as, I did all of the standard stuff, did the pre-compute. My first attempt was with the really small images. He said he tries like 64, and I did that, and the accuracy was pretty bad. Then I pumped it up to 244 with ResNet and had 80%. And then did the learning rate finder. This was kind of interesting. Like if you look at this learning rate and see where it taps out and then back it off, like in theory, I think even like 0.4, 0.5, it still has a pretty decent slope. I tried that. The accuracy was horrible. Any thoughts on that?
I had pretty much the same curve here, and I choose 0.1, and that was pretty good. But also when I did a higher learning rate, that was not good.
Yeah. So I think I remember him mentioning at some point, you know, kind of find before it bottoms out and then back off by an order of magnitude. And I tried to get a little bit more aggressive than that, and that did not work. So 0.1 and 0.01 both worked decently. Then, you know, but I was still wasn't getting the 99.99s that he was showing there. So I tried the ResNext. Did anyone run into trouble getting the other architectures to work? Because there were some hoops that I had to jump through there to download the weights and stuff.
Yeah, we had to download the weights. I also used a different architecture.
Yeah.
So you had to download the weights from Fast.ai library, their website, and then only it could work.
Yeah, I was trying to do that this morning, and their file server kept crashing, so I ended up downloading the weights from the ResNext, the Facebook GitHub, and had to convert them from Torch 7 to PyTorch. But eventually was able to do ResNet 50. And like, this is code that he's running in the video and getting, you know, 0.99. I think I would restart it down here. He's got like this all in one screen and getting 0.99 accuracies, and I'm at 0.88. So maybe my GPU is broken. If anyone has any thoughts on figuring out how to debug something like that, let me know. Anything else that folks ran into? Stumbling blocks? What did you learn and find most interesting?
Well, I really found interesting and very good that last time we had this discussion about the resizing issue, and that really kind of attracted me to look into that and figure out what's happening, and why Jeremy told that it's no problem to have different sized images. And yeah, I think that's what I like about this course, is that you get this kind of oversight, and if you want to, you can dive into the deep things, and I like that.
Yeah. Yeah.
I'm still digging a little bit deeper into it, but I learned a little bit this week about the difference between the images I was working with, which were cartoon images drawn, you know, hundreds of years ago. The difference between trying to classify those and things that are actually in ImageNet, and I've been trying to tweak some settings based on the satellite part of the discussion to see if I can try to find some settings that might work better, since I'm not necessarily working with normal images.
So like unfreezing earlier layers in the network and retraining those?
Yeah, at least there's, it's, I think the size setting again, but there's something a little bit more dynamic this week, and I haven't necessarily landed on anything yet, but I've been playing with it.
Yeah. Who else wants to mention what you've learned, what you found interesting?
Yeah, for me, it was more of, you know, getting the sort of accuracy that I was getting just by writing a few lines of code. I've never participated in Kaggle competitions before. And I tried with 3 different data sets. And just with doing whatever he told, I was, you know, almost getting around top 30% to top 20% accuracy. So yeah, for me, that was like, yeah. So I was actually looking at new competitions that if I can participate in something like that. Now I was getting like this simple confidence, like, yeah, I can probably try my hand at that.
That's awesome. Who else? We've got some more people on here. I think for me, it was like, you know, I'm not fully there yet in figuring out this accuracy issue, but I can see it. It's like within kind of grasping distance. The lesson is kind of, this particular lesson is kind of jumpy. Like I don't know, the notebook that he's using, I don't have it. I don't know if someone's found it. But you know, at one point there's this part where he kind of rattles off the, you know, do these 9 things to create a world-class classifier. And, you know, I think, you know, if I feel pretty good about, like, if I can get those things to work, then, and, you know, I've got this better understanding now about the kind of retraining the different layers and stuff like that. Yeah, I feel like it's close. I just need to figure out some, you know, some things that I'm not able to get to work. And I haven't had a chance to, like, explore the forums and, you know, see if people ran into this reduced accuracy issue. But I definitely, you know, I think I forget who said it earlier, Kartik maybe, you know, this top-down, or Akai, the top-down approach to kind of pull together the big picture, and then, you know, digging into the various pieces, I think has been pretty nice. And there's also, for me, like, there's an element of it where I'm not too stressed if I don't get something, because I know, like, we're going to go back to it later and cover it in a lot more detail anyway. And, you know, all these things we're going to get down to, you know, get down to the math, or at least a strong intuition about why they're working. So you do get to kind of choose where you want to dig more deeply. I remember one question that I had. I wonder if anyone knows the answer to this. When you're kind of training or when you're computing your activations, when you have pre-compute true and you're generating your learn model, does anyone know why there are 3 things here? Is that just a default and you could change that, or it doesn't have anything to do? It's not like the number of layers in the model. I don't know why there are 3 passes as opposed to some other number. Anyone wonder that?
I kind of assume that there's some kind of underlying parameter that's a default.
Yeah. So there's one, and I'm not sure the 141, 36, 179 either. But yeah, that's something.
Number of mini batches maybe, or so how many pictures are inside? How many pictures are in this?
Yeah, this one was 10,000 in the training set. 8,000 in the training set and 10,000 in the test set.
Okay. So how much is it? 141.
So, yeah, what was it? And I think I had 28 at the end there. 292. So yeah, so this is related to the batch size.
Yeah.
And then, but then 73 and 370, I don't know. But that's another thing that I wanted to kind of dig into. So let me catch up on questions.
Maybe this ResNet or ResNext architecture?
This one is ResNext. The previous one I showed was, that's ResNext also, but with a different image size and batch size. This one is ResNet 34.
So maybe that's this residual part that's also calculated. I don't know exactly how it works, but they are kind of extracting some of the feature maps inside the network and then putting it back in this kind of loop. Mm-hmm. So maybe that, I don't know.
Oh, you know, and there's also when there's, There was some suggestion that the network has like 3 parts, because when you do the differential learning rates, you give it 3 learning rates. And so maybe these relate to those 3 different parts of the network. I didn't fully understand that, but he seemed to suggest that there was a beginning, you know, some kind of preconceived notion of the beginning part of the network, the middle part of the network, and the end of the network.
For me too, there's a lot of stuff I don't understand. I think this is also because he throws a lot of stuff in those Fast.ai library, a lot of things that are fairly new and not really used by anyone. But I just like that fact that with a library you can use all those things, even maybe without understanding them initially. But then, yeah, I think it's a good. I like it. I like this approach.
Yeah, yeah.
And
I'm sorry.
I also like to understand that better as well, but I like the fact that I can use already those techniques. Yeah.
Mm-hmm. I'm starting to wonder if maybe Jeremy was like a Perl coder before he started working on this stuff, because he likes like the variable names and the function names to be super compact.
Yeah.
So catching up on the Zoom chat, Hakeem was asking, how big is your data set? That was specific to Kazak's. Data set might be too small. Does Hakeem or Kazak's want to catch us up on this discussion? Matt, feel like Fast.ai abstracts away a lot. Lenny, yeah, for sure. Post on the forums and report back. A little bit too much like magic. Yeah, I've tried to go into the source code a few times to try to figure stuff out. But the things that I've looked at, there's too many, it wasn't really easy for me to, calling out to other things, and it wasn't really easy for me to figure out what was happening. I guess if I had more familiarity with PyTorch itself, I'd know where PyTorch was being called. And, but I haven't been able to get a whole lot out of going straight to the source code. And so it does, at points, feel like magic as well for me. Spectrogram recognition instead of photos, recognition of animal calls from the spectrogram. Is this part of that previous conversation? Did someone work on spectrogram recognition? John is not clear on what test time augmentation does to improve the process. I understand augmentation for training samples, but not test time augmentation.
I think that's probably a pretty Kaggle specific thing. You take the image you want to show to the network, and then you kind of do this augmentation to then combine the probabilities. That's somehow kind of an ensembling. I don't know if that's ensembling, but it's really just to get the last digits out of the network to get a better score. I've never seen that someone doing that in real life, because I mean it's costly in terms of computation.
So test time augmentation, that increases the number of validation samples you have, right?
Train time augmentation, a standard augmentation, it increases your validation samples.
It increases training samples, right?
Right, training samples. And so the I got the impression that the test time augmentation was for inference, but now that you're mentioning validation, I'm wondering if I remember.
I also understood inference.
That was in lesson 1, right?
So the way I would understand the test time augmentation would be pretty much similar way to how is it used in the training. I guess some images will be like Jeremy calls them fat, so like not really square, and those images it will have hard time to predict, right? I think so. When you take a couple of when you zoom in and take some other parts of that image, then it's and then take average of those different versions, I think it's got better chances of predicting in those cases. That's my understanding.
Yes,
I could be wrong.
I understood pretty much the same. But you mean inferencing on test time, so looking at the test set and then getting a better prediction because you show the network different versions of the picture, so maybe he's finding a better version to find a good probability.
Yeah, correct, exactly.
So I think what is happening here in lesson 1 is that the test time augmentation is used at inference time. Is basically you have this image that you want to do inference on, and you make augmentations of those, and then as Kai was saying, you average it out. But then to try to get a sense for to try to measure how effective that is, he does TTA on the entire validation set. So I don't think it's something that you're using in training to expand the size of your validation set. It's just a technique he was using to measure how effective this is, and saw that the accuracy of the validation set when TTA was used was greater than the accuracy of the validation set on its own. What else? What other questions do folks have? Any test time data used to determine cost function, which is then used to guide backprop not yet covered. Having more validation data improves generalization. I think in this case where it is difficult to understand why we are doing TTA without understanding the low-level math. Does regular augmentation not no, that wouldn't, that's on the test, I mean the training data.
Okay, here, so Lenny Johnson said that this is this test time augmentation is used on the validation set during the training phase to backpropagate, so which is measuring the error in the network. So that's used in training. That's could also be.
Is there a setting somewhere that, so learn.tta. Yeah, that it's not clear to me if that learn.tta is actually learning, or is it just spitting out inference on that? Actually, it's not clear to me what that thing is doing.
I would think it's not training at that point. I think training's finished at that point. That would be my interpretation.
Yeah, I mean, there's no like progress bars or anything like that here.
Yes, I think it's done like that. It's for the after the training when you. That's at least what I understood. So when you finish the training of the network, then you do inference on the test set for the Kaggle competition, and there you do this test time augmentation to get more stable probabilities.
Maybe I'm wrong about this. I kind of vaguely remember that part of the issue was that the test images were, I guess, being cropped, and so if they were rectangular, some of the key features might have been taken out. So I think the augmentation might have been to try to get some of the key features back into the crop.
Yeah.
Yeah, there's a couple of places where that comes in. One is that zoom factor, and that augmentation, the other augmentations, but I don't know that that's specific to the test time augmentation issue. So I pulled up the code here for TDA. So predicts with test time augmentation. In addition to original test validation images, apply image augmentation to them like for training images and calculate the mean of the predictions. So yeah, it's not doing, at least as documented, additional training here. It's just predicting accuracy.
Yes, it's for inference, better inference.
Yeah.
Yeah.
So is that consistent with what you were saying, Lenny? Lenny, you were, I mean, and I can imagine that you could build into your kind of training validation routine the use of TTA at validation time and use that as part of your training loop, I suppose. But I haven't seen any indication that the Fast.ai library is doing that, if I'm understanding correctly. So Lenny, is that what you think is happening? Right. So Lenny said, maybe right, that it's not affecting training, but giving us a better idea how well the network is generalizing. Yeah. All right. What other questions have come up?
Last time someone asked if there's a documentation, and I just found they just started to build a documentation, and I found there's one markdown file where some of the architecture of the Fast.ai library is described. It's inside the GitHub repo, so maybe that can help to understand how the library is built.
Do you have a link to that?
Yeah, I will.
I had come across one, but it was very, very basic.
Yeah, it is. There is a docs folder in the Fast.ai repo. I'll post a link. Just a second. I'll post it in Slack. I can't paste the link into the chat.
Is it this this project that is an approach page?
Yeah. And when you scroll, when you go into the docs folder, anatomy.adoc. Yeah, there's some explanation of how the library is built. Maybe that helps.
Oh yeah, yeah. I also found an article that looked interesting. What's this thing? This one here. I'll put the link in the chat. 3 lines of code deciphering Fast.ai, and it kind of somewhere down here talks about, is this the one? Just talks about the different, consists of 27 scripts, and the author specifically identifies 4 of the Python modules that were particularly helpful in kind of understanding what was going on. and then kind of goes into, I mean, we know most of this stuff already from the lesson. But I thought that was at least narrowing down some of what you need to look at to understand what's going on here. All right. Let's see. Any other questions?
There's also like a wiki page seems to be, but seems like it's not really updated anymore. I just pasted a link to that. Seems to have some information in it, but maybe it's even the version 1 of that course. It doesn't seem to be updated recently.
Yeah, there's another. Is the wiki the other?
Yeah, this is the different one of the lesson wiki, though.
Yeah.
They don't refer that anymore anywhere. So I guess it's kind of abandoned project. But
Yeah.
Other than that, it's got a lot of information in it.
I think Jeremy said that they are using the forums. You can make wiki pages in the forums now.
Right.
And I think this one is the where they use Keras and not PyTorch.
Yeah, that could be the case. Yeah.
So last year, I think.
Yeah. Yeah, I've generally found the wiki pages for the lessons and the various links off of those to be pretty useful. I'm assuming you all saw this, this lesson, it says lesson 1 notes, but I think it was linked to in the lesson 2, and it goes through and like provides detail for all these parameters like annotations for different things that were going on. It's kind of interesting. All right, cool. Other questions? Has everybody posted their knowing what exactly to post in this one is a little bit more difficult than lesson 1, but I'd love for folks to post like which of the data sets they worked on and maybe what accuracy they got to. And so we can all have a sense for who's working on what. And then I'm not sure if we continue on in the same, I haven't looked at what lesson 3, what direction lesson 3 takes this yet, but I'm hoping to spend some more time on this and try to get my accuracy up before moving on to lesson 3.
I think he starts with explaining how convolutions and filters and stuff like that work. I just watched the first few minutes.
Okay. Cool. Any other thoughts, questions, ideas? What is the link for this lesson with notes? So that is in wherever the Fast.ai wiki, the lesson wiki thing is. Wiki lesson 2. Annotated notebook. It's one of these lesson resources here. All right, cool.
Just one quick question. Have you tried to saving the, so after you train the model, saving the model to the learn.save and then loading that model? I've tried that, but never worked for me. So I'm doing something wrong, but I wonder what anyone tried that and if that worked for you.
Did you get an error or did it just not do anything or not?
Yeah, it wasn't giving. Yeah, I don't remember now. Was there an error? Yeah, for sure it was not working as I wanted to be. I was training like for 5 hours, so I saved the model, and then when I wanted to get it back, it just was not there or was giving me an error. So I wondered whether you guys had the same issue or maybe I'm doing something wrong. Because that would make sense for stuff like when you train for a couple of hours to indeed to save that and not to repeat that 5 hours training. I had that with the one cargo competition, and it was driving me crazy every time I had to restart from. And also I was using Paperspace that time, and it was crashing from time to time, and that was also frustrating. After a couple of hours of training, it just crashed. So saving would make a lot of sense, yeah, but just couldn't make it work.
I don't know what possibly happened, but you can try to maybe do a git pull. Maybe there was a bug or something.
Kind of when you just kind of do everything from start and train and then click save and then load, it kind of seems like it's working. But then I come back to the same notebook like next day, and I want to just load it without training. It didn't work. So I need to look how to use that, because I think that's quite useful thing to have. Yeah.
What was that? What was the exact method?
There's a learn.save, and then you type a name, how you want to save it, and then learn.load, something like that, I think.
Guys, I have to leave now. So see you next week.
Thanks. See you later.
Alrighty. See you. Bye-bye. Yeah, this looks like it's from PyTorch, and so maybe there's something else that needs to happen. It may be something, a separate thing that has to be called in order to actually persist it to disk. Maybe this is saving it in memory or something.
Yeah, indeed. I need to look at it. Yeah, look at that.
Yeah. All right, cool. Well, thanks everyone for hopping on this morning. Let's keep it up, and we will reconvene, of course, in Slack and next week here.
Great. See you next week.
Bye-bye.
Bye, guys. Take care.